Chapter 11. We're now transitioning to throw your calculator away. It is non-calculator time here, which is the remainder of the chapters. Don't throw it too far because you'll need it for like exam 3 and the final. But for none of these chapters coming up, there's pretty much no calculations. So if that was the part of the class you're waiting for, we have arrived here. So we're going to start talking about organic chemistry now. And organic chemistry, pretty much the first line in any organic sort of book is the study of carbon, basically. So really, organic compounds are oftentimes the root or the basis of all organic compounds is a basic connection between carbons to carbons, and basically hydrogens attached to those carbons is really the basic sort of setup of all organic molecules. As we'll talk about as we go through some different chapters here, what happens along the way is we replace some of the hydrogens with some other elements like oxygen, nitrogen, sulfur, maybe a halogen, and we do create some different organic compounds. But the core basis pretty much of all organics compounds is pretty much this sort of connection. It's always carbons to carbons, and then really hydrogens attached to those carbons, again, unless obviously something has replaced it. So the importance of sort of carbon is this: carbon pretty much will want to always make 4 bonds. So in organic compounds, it should always be 4 bonds to carbon. And I say that because when people start drawing organic compounds, I don't know, they just keep liking to add bonds. And, you know, before you know it, carbon's got like 30 bonds to it, which is a little bit too much. Yeah. So it definitely needs to get to 4. It should never have more than 4. Kind of like hydrogen, if you're putting dots around it and double bonds and triple bonds, it is incorrect. Same thing here with our carbon. Again, if you got more than 4 bonds, it is definitely probably incorrect. Also, that is a good reminder for hydrogen as well, as we've talked about many, many times. That is pretty much what hydrogen should look like when it is bound. There should be no dots around it, should be no double bonding to it, triple bonding, or anything like that. It should only look like that, as hydrogen, as we talked about, only needs to get to 2 electrons, which means it makes basically 1 single bond. The other important aspect of this, as we'll talk about as we continue on here, is that carbon-hydrogen bond. If you remember from our bonding chapter, that is a nonpolar bond. The difference in electronegativity is something like 0.4, which is like your maximum limit for it being a nonpolar bond. What that essentially means is it will basically share those electrons equally between the carbon and the hydrogen. And obviously, if we have our carbon to carbon sort of bonding happening, that bond is also nonpolar. And that's a very important property of a lot of organic compounds, especially hydrocarbons, like we're going to talk about in this chapter. They're pretty much nonpolar, which means they work really well with other nonpolar things and not so well with things like water, which is polar. So things that have very similar interactions with each other are very soluble in each other. And in this case, a lot of organic guys are sort of insoluble in water because water is polar. A reminder in terms of solubility, it is based on sort of their ways that they can interact with each other. So things that are polar and polar are soluble in each other. Things that are ionic and polar are soluble in each other. Things that are nonpolar and nonpolar are also all soluble in each other. Again, if you cross over and do a little polar, nonpolar action, that's going to be things that are insoluble in each other. That's why if you ever seen an oil spill, for example, oil is basically all carbons and hydrogens together, which is nonpolar, and basically it will just start floating there on the water because they will not mix. Our oil and vinegar salad dressing, right? You mix it up and eventually they will all kind of separate out from each other. Typically, the oil goes to the top like we kind of see here. And the water is usually the bottom layer as to what you have going on. Any questions on that there? So as I mentioned, organic compounds, the basis of it is really, as I said, that carbon to carbon interaction and that carbon to hydrogen interaction. But we get a lot of different types of organic molecules that can be created by, along the way, really substituting out, if you will, some of those hydrogens for other elements. So very common other elements we see a lot in organic chemistry. Oxygen finds its way into the organic molecules. Sulfur, nitrogen, any of those sort of halogens or phosphorus. When they find their way in, it actually does sort of change sometimes the properties of that organic compound to perhaps being something that is going to be soluble in water based on if there's an oxygen and a hydrogen there. It can really sort of change the aspect of that molecule and give us some different properties. So as we sort of insert these different sort of elements along the way in organic chemistry, we'll get different types of organic compounds, and they will have different properties. So there are definitely organic compounds that are soluble in water, mixes well with water, and there are some that definitely does not. And it really does depend on sort of what elements are present and the ability of those guys basically to interact with each other. Organic compounds will typically have covalent bonds, which means they are typically sharing electrons because, again, the basis of it is basically carbon and carbon, which are two nonmetals, which are going to share electrons, and carbon and hydrogen, which also are two nonmetals, which will share electrons. Typically, because of the way they are held together, organic molecules are held together for the most part. Basically organic molecules that contain carbon and hydrogen for sure, they're held together between each other by a force which is known as a dispersion force. And a dispersion force is a very weak, what is referred to as a intermolecular force. I think maybe we talked about this way back when in one of those chapters, I think, intermolecular forces. But intermolecular forces are the forces that basically hold one molecule together with another. So it is the force that holds, for example, like one organic molecule with another one of itself. Or like, say, if we're talking about water and water together, it is the force that basically holds all those individual molecules together, not individually, but one molecule to another. And that's different than, say, an intramolecular force. Intramolecular force is the force that holds basically the single molecule together. So for example, if you took something like water, the oxygen hydrogen bond where they're sharing electrons, which is the covalent bonding, that's an intramolecular force within the single molecule, and that's what holds the one water molecule together. But when you get two water molecules together, water is polar, so oxygen is positive, hydrogen is negative, so they are held together by hydrogen bonding, which is a intermolecular force. And that's what holds this whole water molecule basically together with that whole water molecule. Intermolecular forces are always weaker than any intramolecular force. And you know that by heating water, if you ever boiled it to make pasta, what happens is when you heat up the water, it is the intermolecular force, thank you, the bond between the two water molecules that break, that make it go create steam, water in the gas phase. If it was the opposite and the intramolecular force, the individual OH bonds were weaker, when you would heat up water, you would get hydrogen gas and oxygen gas formed, and you'd probably never get to the pasta part, which would not be good. So what happens is the intermolecular force actually breaks apart. How this relates again to organic compounds is they're held together by pretty much the weakest known demand intermolecular forces. That's why a lot of organic compounds and hydrocarbons, some of which you may be familiar with, they are like gases under normal conditions. Things like methane, butane, propane, those are all gases because the force that holds those two molecules together is a relatively weak one, and they're able to basically, it doesn't take a lot for it to just kind of come apart and go into the gas phase. So typically the weaker the force that holds a molecule together with another molecule, the much easier it is to go into the gas phase. And that's why a lot of organic ones, especially the early ones there, a lot of them are gases. Also why when you deal with a lot of organic chemicals, if you ever do a real organic sort of chemistry class or something like that, they oftentimes will put you in fume hoods when you do the organic part, because a lot of organic compounds are what are referred to as being volatile, which means that pretty much it doesn't take a lot for it to just simply go into the gas phase really, really easily. And usually you don't want to do that in an open room. You kind of want to do it in the fume hood when you do those type of things. And that's also because a lot of them are flammable as well. So they could go into the gas phase really easily. And if they're by a fire, that's not a very good thing. As you know, with a methane, propane, and butane, methane, again, is what comes out when you light your Bunsen burner, right? You just need a spark and it will catch on fire, right? So it's very, very flammable. Same thing with propane or butane. Your barbecues and stuff like that. As I mentioned before, it typically is not soluble in water, again, because water is polar, and most organic hydrocarbons are non-polar. So you got that interaction where over the long period of time, what happens is something like water really wants to do hydrogen bonding, but something like an organic guy cannot do it. So they could both kind of do a little dispersion forces for a very short period of time, but over the long haul, there's no way for those guys to basically stay together. And that's why, again, if you think about like an oil and vinegar sort of salad dressing, at some point they will not be able to maintain that sort of mixture, and they will basically separate out from one another. Also, why if you know kind of mix the oil, even though oil goes down in the water, it'll eventually kind of work its way back to the surface, because there's no way for them to maintain that interaction over a long period of time. And that's very different than inorganic compounds, which are pretty much like ionic compounds. Ionic compounds are held together by very strong electrostatic attraction between a positive ion and a negative ion. And these guys are typically so strong that they typically will never go into the gas phase. Even if you heat them up really, really strongly, they will actually just start melting before they'll go into the gas phase. But definitely an organic guy very, very easily can kind of go into the gas phase because of those weak interactions that occur. Here are some properties of organic versus inorganic. Again, organic, we have sharing of electrons. Inorganic, we have the electrostatic attraction. Typically speaking, melting points and boiling points for organic compounds are very low compared to like ionic compounds. And also, as you can see, the flammability is also very opposite as well. Very high in organic compounds. And again, like I said, salts and stuff like that are typically not very flammable. All right. So for each of these, the most typical compounds are going to be inorganic or organic. Things with high melting points should be inorganic, as things like our salts. It's not soluble in water. That definitely is going to be an organic. Has the form of carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. That pretty much is an organic compound there. This is an ionic compound, which would be inorganic. It burns easily in air, should be organic. And it has covalent bonds, also should be organic as well. Again, inorganic guys like ionic compounds, again, don't share electrons, they transfer electrons. And again, it's that positive negative attraction like we've talked about previously. Any questions on that one there? So let's talk a little bit about hydrocarbons. Hydrocarbons, much like the name implies, is basically a compound that contains carbons and hydrogens. And once again, the connectivity that we see is always carbons to carbons, and again, hydrogens attach to the carbon. Pretty much hydrogens are used, you could think about it this way, as we talked about before, carbon needs 4 bonds. So pretty much along the way, if you are done making all your bonds and there's nothing else left, but carbon is short bonds, it's probably going to be hydrogens that should be attached there to get it to 4. And in an organic molecule, again, this is our carbon. It's got its 4 bonds to hydrogen here, and that is a nonpolar molecule. That is a tetrahedral geometry. That is 4 electron pairs and 4 bonds, which is tetrahedral. And it is no dots on the central atom, and everybody on the outside is the same. So it will be a nonpolar molecule in this case. Now, you sometimes hear the term saturated hydrocarbons. Saturated hydrocarbons pretty much means each carbon has the maximum number of hydrogens it should have. So that's what a saturated hydrocarbon is. The only really way to achieve a saturated hydrocarbon is they pretty much all need to be single bonded. So all the carbons has to be single bonded. You cannot have a double bond or a triple bond. Everything needs to be single bonded. So when we look at this guy here, each of these carbons basically have the maximum number of hydrogens that it should have. It has basically 1 bond to the carbon, which means again needs 4 bonds for each. 1 bond, 2 bonds, 3 bonds, plus the bond, the carbon is 4 bonds. And same thing here, 1, 2, and 3, and that 4th bond to the carbon. So each of the carbons here are saturated. As we'll talk about a little bit later on, unsaturated means that it doesn't have the maximum number of hydrogens that it should have. And that basically means that there's probably a double bond or a triple bond that's there. Because in organic chemistry, as we will see, pretty much what will happen as we draw our saturated hydrocarbon here is as you make a double bond, let's say we wanted to put a double bond there between the 2 carbons. If I put a double bond between the 2 carbons, but left everything just the way it is, would this be okay? This would not be okay because each carbon now has 1, 2, 3, 4, 5 bonds, which again is not 4. It needs to be 4. So every time you make a bond, either a double bond or a triple bond between 2 carbons in an organic compound, what always happens is each carbon loses a hydrogen to basically make room. So this guy would lose a hydrogen, and this guy here would lose a hydrogen. And now we have this guy, which has a double bond. And he still has only 4 bonds to each carbon. But because of that double bond, this thing now becomes what is referred to as being unsaturated. It does not have the maximum number of hydrogens as it should, as opposed to this guy, which is saturated. Now, if I wanted to throw a triple bond between the 2 carbons, I would once again have to sacrifice 1 more hydrogen from each carbon, and that would leave me just 1 hydrogen on each. So pretty much every time you lay up a line between the carbons to make a double bond or a triple bond, you sacrifice a hydrogen on each carbon, and that's where basically the bond will sort of come from, if you will. This guy up here would also be unsaturated as well. So that guy would also be an unsaturated hydrocarbon. But saturated hydrocarbons basically are all carbons that have single bonds. And because they all have single bonds, that essentially allows them to have the maximum number of hydrogens that they should have. Any questions on that there? So here's methane and a few different ways that we could represent methane. Methane is pretty much your simplest organic molecule you could have. It is 1 carbon with basically 4 bonds to it. And as I mentioned a second ago, there's a couple of different ways you can write it. This is the formula, the molecular formula here. This is drawn out kind of like a Lewis structure here where we show all the bonds to hydrogen. This is sometimes what is referred to as the expanded structural formula. Again, that's sort of a computer modeled formula. This is some wedges where the sort of dashed line is going behind the paper. The wedge is sort of coming out of the paper, sort of showing the three-dimensionalness of it. But pretty much all saturated hydrocarbons will have this tetrahedral geometry because they all have single bonds, which means each carbon will have 4 bonds and 4 electron pairs. So in a saturated hydrocarbon, you will expect this tetrahedral geometry to occur, which again is sort of this triangle on each side, having that bond angle of 109.5 like we talked about when we did bonding. Now this is ethane, which is the second organic molecule you could have. It has 2 carbons. And to illustrate a couple of other ways that we can write these things, we could write it like we did here, C2H6, which is the molecular formula. We could draw it out like we'd see here, which is the expanded structural formula. And another very common way that we could write formulas in organic chemistry is what is sometimes referred to as the condensed formula. And the condensed formula, pretty much you just don't draw out the hydrogens. So you do everything but draw out the hydrogens. So CH3 dash CH3 would be the condensed structural formula. Now, you do need to remember that when you write sort of a condensed formula like you write there, CH3, maybe even CH2 for something else here, CH3. This is an example of a condensed formula for propane, not ethane. But the connection here is still carbons to carbons. So sometimes people, when they see this written like this, think the hydrogens are in the middle. And remember, hydrogen can never be in the middle. So for example, here, if we were to draw this out, you should always connect the carbons to the carbons. And again, all those hydrogens should go on the outside there attached to the carbons. So although in condensed formula, we sort of sometimes will show the connection kind of between the hydrogen and the carbon, this here represents this. So if we look at it, this is CH3, that is the carbon and 3 H's, which is CH3. If we look at this, which is CH2, that is a carbon and 2 hydrogens, and that is CH3, which is a carbon and 3 hydrogens. So that is, again, the way that it is connected and related to each other. But sometimes people, when they see the condensed formula, sort of mistake how the connection sort of works. Any questions on that? By the way, another sort of important formula that we will see is what is sometimes referred to, and we'll go maybe here-ish, come back this way, is what is sometimes referred to as line structure. And line structure is pretty much what it sounds like. It is just lines, something like that, yeah. So that is line structure. And in line structure, you pretty much don't draw anything out unless you need to put the element there. But what this represents is at each of the starting points and the points in between, these are all carbons, basically. That's carbon, carbon, carbon. And each of the carbons is assumed to have the proper number of hydrogens, which means this guy at the end would need 3 hydrogens to get the 4 bonds. Guy in the middle would need 2 hydrogens to get to 4 bonds. Same thing with this guy. And guy at the end would need 3 hydrogens to get the 4 bonds. So line structure is basically just lines. It's sort of a clean way of drawing things. But pretty much anywhere a line stops, anywhere 2 lines come together is a carbon. And again, it should have the proper number of hydrogens. If we were to draw the expanded formula for this, it would be this. And that is that is what this represents basically that. It's the same thing. So line structure is used a lot in organic chemistry, and it's sort of a minimalist sort of structure, if you will. But it's kind of a clean structure as well. So just to give you reference points here, this guy right here, this carbon would be this carbon. This carbon here would be this carbon. This carbon here would be this carbon. And lastly, yeah, we'll do red. Red's not a choice. This carbon right here would be that carbon right there. So that is the relationship of what it really looks like if you drew it all out from the line structure. Again, you can see each of the carbons would have the maximum number of hydrogens in this case to get to 4 bonds. Any questions on any of that there? Now, in a line structure, if there is something other than carbon at the end of it, they will actually write the element. So they'll actually write the element at the end of the line if there is something other than carbon that should be there. But if it's just carbons and hydrogens, it pretty much will just be lines when you look at it. So for example, if we had something like this, and we had like a BR. So at the end of that line, obviously it's connected to a bromine. Everybody else there would be carbons. So again, this would be a carbon, that would be a carbon, that would be a carbon, and that would be a carbon. And then obviously the guy at the end there would be just a bromine at the end of it. Any questions on that there? Now, sometimes you do have just a line at the end like this. And if you do see sort of a line by itself with nothing at the end, that again is going to be a carbon. So that would actually be a carbon at the end of that line that has nothing else written there. So in this particular case, this would be a carbon, that would be a carbon, that would be a carbon, that would be a carbon. And at the end of the line there would also be a carbon. All those carbons would have the appropriate number of hydrogens to get the 4 bonds, basically. Yeah. Any questions on that there? Okay, so these are some ways that we could represent some formulas. In butane here, predict the shape around each of the carbon atoms. So this would be just like we did when we were doing geometry. This carbon atom here has 1, 2, 3, 4 electron pairs, and also 4 bonds, which means it should be tetrahedral. And by the way, every single carbon there should be tetrahedral as well. This guy right here has 1, 2, 3, 4 electron pairs and 4 bonds, tetrahedral. This guy, 1, 2, 3, 4 electron pairs and 4 bonds would be tetrahedral. And this guy here, 1, 2, 3, and 4 bonds, which would also be tetrahedral. So every single carbon here would have the tetrahedral geometry. That is why when you draw line structures like I did a second ago, and we draw the line structure for this guy, it has what is sometimes referred to as the zigzag shape. And that's because each of those carbons are tetrahedral their way in that. And what it creates is this sort of zigzag up and down, which is why when you draw line structures with a carbon backbone, you typically do this sort of zigzag back and forth, because each of those guys have sort of the tetrahedral geometry when they're all single bonded. So that's why it kind of does that up, down. It's the tetrahedral arrangement of each of those carbons together. Any questions on that there? So let's talk a little about alkanes. Alkanes are pretty much the simplest organic molecules you can have. They are all guys that have double bonds. No, they are all guys that have single bonds here. So these are single bonded carbons. Now, when we talk about organic compounds and different types of organic compounds, there is something that is sometimes referred to as the functional group. And the functional group in an organic compound is really the part of the molecule that makes it a certain type of organic compound. So for example, some people will say that alkanes functional group is the carbon-carbon single bond. So the carbon-carbon single bond is what makes it a alkane, and that is its functional group. When you have, say, a carbon-carbon double bond, it's no longer an alkane, it's what is known as an alkene. When you have a carbon-carbon triple bond, it is now an alkyne. So there's this part of every organic molecule where it has maybe a small part, maybe a little bigger part, but there is a part of an organic molecule which basically allows you to classify that organic molecule as a certain type, like an alkane, an alkene, an alcohol, whatever it may be. There's this one little part of this organic molecule that basically is kind of like its classification. Oh, I see that's there, so this is this type of organic molecule. The other important part of that is we're going to talk about reactions and sort of how these things react. Pretty much all reactions occur where the functional group is. So where the functional group is always the part of the molecule that's really important. It's always the part where pretty much all the activity occurs, all the reactions occur where that functional group is located. Now, alkanes have a general formula of CnH2n plus 2. What does that mean? It means that the N is the number of carbons. So if I have one carbon, for hydrogens, I would have 2 times 1, which is 2, plus 2 is 4 hydrogens. And that is what is known as methane, as we saw. If I have 2 carbons, 2 times 2 is 4, plus 2 is 6. That guy should have 6 hydrogens, and that is what is known as ethane. If I have 3 carbons, 3 times 2 is 6, plus 2 more is 8. That guy should have 8 hydrogens, and that is what is known as propane. These are all alkanes. These all end in what name? A-N-E. Yes, propane, methane, ethane. We could continue on with C4. 4 times 2 is 8. 8 plus 2 is 10 hydrogens. That is what is known as butane, A-N-E. 5 of them would give us 12 hydrogens, and that is what is known as pentane. And there's hexane, heptane. We'll continue on in just a second, but they all end in A-N-E, and that is also how, if you see the name, you know it's an alkane, you know it is single bonded. It's a pretty good way to know that. Now, why are the alkanes really important? We're going to talk about the first 10 alkanes. Pretty much it's all based on those 10 names. So there's going to be 10 names for the alkanes. These are 5 of the 10. Pretty much everything else all comes back to these 10 names. Every other organic molecule known to man, kind of comes back to these 10 names. So it's really important as we go through these organic chapters that you get a really good handle on the first 10 names there of the alkanes, because everything just comes back to those names. We change a little bit on it and it becomes something else. So everything falls back to those 10 names. Now, alkanes, as I mentioned, are hydrocarbons that only contain carbon-carbon bonds and carbon-hydrogen bonds. They are formed in a couple of different ways. They can be formed in a continuous carbon chain. And a continuous carbon chain is like it sounds like. It's just one carbon after another in a straight chain type of situation. Like this. And again, all these guys are hydrogens. We could also have alkanes, which are sometimes referred to as branched alkanes. And branched alkanes are like a tree. Every so often, there's kind of a branch that comes off the main part of it. So you got like your main part of your tree here are your organic molecule. And down the road there there's this sort of branch that comes off of it. And it also obviously has hydrogens attached here as we go across. So this would be kind of like perhaps your main part of it. And then we got this kind of branch that comes off of it, off the main part. And that's what's sometimes referred to as a branch chain. Alkanes and other molecules could also wrap themselves up in like a ring type structure where they kind of just close in on each other. So you can have a alkane or other type of organic molecules that sort of close in on each other and make a ring type structure. Like this guy here, this is what is known as cyclopropane. It basically makes like a triangle type shape there if you do like line structure, where each of these are carbons. So those are three very common ways that organic compounds sort of end up. Just a long continuous chain of nothing but carbons and hydrogens together, a nice long continuous chain where there's branches that may come off in other directions, like on a tree, or they may just decide to kind of close up on each other and make sort of a ring type structure, which would be kind of like that guy over there. When we name organic compounds, we usually follow what is known as the IUPAC way of naming. That's the International Union of Pure and Applied Chemistry, hence the abbreviation. And that is kind of like the formal way that you're supposed to name organic compounds is through the IUPAC way. What you will quickly learn as you go through organic chemistry is, there's frankly multiple ways you name the same compound. So most people, and what we will use in most cases in this class, is the IUPAC way of naming, kind of the official way of naming. It's those three guys in a room to decide for poor chemistry students how you're supposed to name all these things with the weird rules. But there are historical names that are commonly still used for organic compounds. And there are like common names that are also still commonly used for certain organic compounds. So for example, you could have one organic compound that has basically three names that are still very commonly used as you go through it. So for example, if you had something like this guy here, which is actually an alcohol. So this guy here is an alcohol, and this is what is known as, officially, it is actually 2-propanol. This is also known as isopropyl alcohol, and it's also known as rubbing alcohol. Yeah, so that is all the same three things. So there's a lot of very common organic compounds that have multiple names that people, still sort of use along the way here. Yes, and you will know how to properly name that shortly. Yeah, it's scary. You will come across that. We do use sometimes Greek prefixes to name some carbons that go from kind of 5 and on. So as we stop there with pentane, then we have hexane, heptane, octane, and nonane, and decane. So here's a table from your book of the first 10. And once again, it is important to know the first 10 names and the formulas that go with it, because everything is based off of it. I will say, I believe the line structures here are off. They all go to the one below it, I believe. So maybe it's better in your book, but in this slide, they got moved wrong. So the line structures actually go to the one below it, I think, in each of these cases. So let's make sure, again, we did our 1 carbon, which is methane. We did our 2 carbons, which here would be ethane. We did our 3 carbons, which then would have 3 times 2 is 6 plus 2 more is 8 hydrogens, which is propane. We have our 4 carbons, which will then have 10, which is butane. We have our 5 carbons, which then 5 times 2 is 10, plus 2 more is 12, which would be pentane. We have 6 carbons, 6 times 2 is 12, plus 2 more is 14 hydrogens it should have. That is hexane. 7 carbons would have 16 hydrogens. That is heptane, ANE. 8 carbons would have 18 hydrogens. That would be octane. 9 carbons would have 20 hydrogens. That would be nonane. And 10 carbons would have 22. We'll try that again. 10 carbons would have 22 hydrogens. That would be decane. So they all, as you can see, end in ANE. And that is definitely the first thing that you want to make sure that you do, which is learn those 10 names. Because trust me, I am not lying to you. Everything is based off of those 10 names. So the quicker that you know those names, the much happier your organic journey here will be as we go through these different chapters. Any questions on any of that there? Literally, how you go about naming things is, frankly, you count how many carbons there are and go, oh, there's like 4 carbons, so that's butane is the base of the name. So those are things that, you know, you got to be able to kind of count and associate how many carbons there are with the proper name. Any questions on that? These are all single bonded, as you can see in the picture. They're all carbon to carbon attachments with the hydrogens attached to the carbons. And obviously, here's our line structures for each of those guys. So as I talked about earlier, another very common sort of formula that we see is this condensed formula. And again, this would be our 1, 2, 3, 4 carbons, which would be butane. Once again, sort of the line formula of that would look something like this, which has 1, 2, 3, and 4 carbons. Usually you don't put the circles, but there's circles for the carbons there. So again, usually it's just that right there. Yeah.
So on these formulas that you have, like I'm looking at the last one as well.
Mhm.
It's CH3 with the bond CH2 and then bond CH. There's a line that goes down. So it doesn't matter where they go. So when we just count all of them, it's all the same.
We're gonna get into how, if you're asking how to maybe properly name it, there is a method to what you need to do to properly name it. But they're all carbons, if that's what you're asking, if there's nothing else drawn there. But there is sort of a way that you go about counting to properly name something, and we'll get into it in just a second. So maybe that will answer the question that you have, I think. Okay. Other questions? Okay. So here's again the expanded where you draw it out, the condensed. Now, sometimes people will show in a condensed formula a line to represent another guy kind of coming up there. And that's usually a pretty common way of sort of writing something where it sort of has a branch off of the main part of it. You typically would not, in a lot of cases, just write CH3, CH3, CH, CH3 without some way of distinguishing these guys. So this would imply that there'd be too many hydrogens kind of there in this thing, and they're all kind of straight chain. So usually it's a good idea if it is something that's not part of the kind of biggest part of the longest carbon chain, and it's sort of a group that's attached or like a branch, that you kind of draw it even in a condensed formula situation. For example, if we also had like some other element attached there, say something like this, where it's a bromine, for example, that is typically the way that you would probably want to represent it. You probably would not want to represent it like this, as it sort of implies that the bromine is just all in a row with everybody else, and it's not really, you know, kind of off of the main part of the chain without doing some type of parentheses or something like that. Sometimes people will do, but this would be the best way to represent, you know, something that is, there's in an organic molecule, there is kind of a main part of the molecule, which is the main backbone of it, and then off of that is everything else is attached. It's not part of the main part of the compound. How you find the main part of the compounds we'll talk about is you find really the longest continuous carbon chain, and that's the biggest part of the molecule, and that's really kind of the backbone of that molecule. So if something's not really part of that really longest continuous carbon chain, when you're drawing something in condensed form, it's usually kind of appropriate just to draw a line out and sort of make it different than the main part of the chain like we did there. Here's the skeletal formula, which I call line structure, and most people call line structure as well. But usually, again, you really don't write any of these things out. You just, sort of draw things like this. So for example, this guy has how many carbons here? That just true. It has, if we were counting carbons, that would be a carbon there, 2, 3, 4, 5, 6, and 7. And that would be heptane, right? That's all carbons and hydrogens basically there. Again, at each of these carbons, there would be the appropriate amount of hydrogens, which also is not usually drawn in line structure as well. This guy would have 2 hydrogens. This guy would have 2 hydrogens. 2 here. And I'm counting the hydrogens here just again to remind you, carbon should have how many bonds? 4. So this carbon at the end has 1 bond coming into it and would need then 3 hydrogens to get the 4. So that's how I get the 3 hydrogens at the end. Just like this guy here in the middle. This guy here in the middle has 1 bond coming in, 2 bonds on that side. That is why he only needs 2 hydrogens to get the 4. So we kind of use hydrogen to get ourselves to 4 bonds for carbon, but we do need to still count the bonds, obviously, between the carbon and the carbon, and that tells you the appropriate number of hydrogens that you should have. Bless you. Any questions on that there? So here's just some different representations of formulas and condensed formulas as we see here for butane. That's the expanded one up there. Here's all different sort of condensed structures. So why are all these the same, even though you may look at all these guys in the middle and go, they kind of look like different things, right? They're drawn differently. So one of the most important things when you look at an organic molecule that you need to do when you go to, for example, name it, is you need to find the longest continuous carbon chain. And what that means is you basically start at 1 carbon and you keep going until you hit a dead end. The only thing you cannot do is you cannot backtrack. So you can't hit a dead end, come back, go up and over. It doesn't always has to be the straightest. It could go straight, come up, go over, go up, go over, come back down. The only thing you need to do is start in one location and end in the next without backtracking. So again, when you look at the middle there, you may think, they all kind of look really different. And this is a very common thing that people do when they are asked to draw, for example, isomers, which we'll talk about. But if we start here, for example, that is 1 carbon, 2 carbons, 3 carbons, 4 carbons. That is butane. We start here, which looks different on this guy. That is 1 carbon, 2 carbons, 3 carbons, 4 carbons. I didn't back up or stop. That is still butane. It just looks different. You drew it different. This guy here, that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, still butane. Every single one of these, 1 carbon, 2 carbons, 3 carbons, 4 carbons is butane. So even though they all look completely different, even this guy here, right? This guy here looks a little different, but if you start here, that's 1 carbon to 2 carbons to 3 carbons to 4 carbons, it's still butane. So even if it may be drawn weird, 1 carbon to 2 carbons to 3 carbons to 4 carbons, it is still butane in this case. And just to finish out, 1, 2, 3, 4 is still butane in this case. So when we talk about finding the longest carbon chain, it is that continuous carbon chain. And again, it may not always be the straightest. It may branch out. Again, the only thing you can't do is back up and go back the other way. So you got to go from one end till you hit a dead end. And you always want to try multiple options because there could be multiple ways to get to the longest carbon chain, and is not always the straightest one is the longest carbon chain. Any questions on that? So again, even though all those things may be drawn differently and you may perceive them as being different things, they are all exactly the same thing, just drawn differently because they all basically have 4 carbons as its longest carbon chain. Yeah. You got to pick one and go and just start counting. Yeah. So you pretty much got to pick one and go. So for example, let me just randomly draw one here and see how bad I do. All right. So let's do this guy here, and I won't draw out all the hydrogens, so I'll just do a condensed structure here. So let's do this one. So you take a look and you decide what is the longest carbon chain here that is a continuous carbon chain. You want to try all your options. I guess I should put a H3 on that guy there. All right, I heard 7. So let's see. So if we go straight across, which, it's a good place to start. Why not just go straight across and see? We got 1, 2, 3, 4, 5, and 6. So that's not bad. All right, so that's 6 going that way. See if we can do that right. There we go. Let's then go straight this way. I see an error real quick. Let me just fix my bad organicness. All right, there we go. All right, so if we then go actually straight and decide, let's go down maybe here. So we go 1, 2, 3, 4, 5, and 6. So that's 6 as well, right? So that's another potential option. So to answer your question, you see we're just trying pretty much every option we have. We then could go perhaps an option that maybe you didn't see as well. This would be 1, 2, 3, 4, 5, and 6. That's also 6. So that's 6 still tied as the longest. And I'm just going to demonstrate all the options here so you can see them because it's always good to see them. We could also go 1, 2, 3, 4, 5, 6 this way would be a possible chain. So that's still 6. We could also then go 1, 2, 3, 4, 5, 6, and 7. So that would be our longest carbon chain here. We went through all the different options, and you do want to do that. As you also saw on this one, there could be options where, you went straight, you got 6, you went straight and down, you got 6, and that's okay. And the key here is you could choose any way you want. Sometimes it's easier if you just take the straightest because you kind of see everything else. What I just highlighted there, by the way, would be the longest continuous carbon chain, and that was 7. And the base of this name would actually be heptane, right? Because that is what 7 carbons is with all single bonds. What is attached over here is not part of the main chain. So this is what is referred to as a group. And a group is maybe a group of guys like that, or carbons that are attached, which are not part of the main chain. And they actually have special names. For example, I randomly drew this, but this one actually has a special historical name, which is known as the isopropyl group. And that is a CH3 CH group, which is basically what we have here. CH3 CH CH3 there, I think. Yeah. All right. So this actually would be called, if we were to name this properly using IUPAC way of naming, we have the longest carbon chain, which is the base of our name. The next thing that you're supposed to do is identify the groups that are there, which in this case is what is known as the isopropyl group. Organic chemistry and naming, it's all about telling people locations of where everybody's at. So when we have a long chain like this, what we can do is actually number the long chain, the carbons that are part of it. And there's really two ways you can number this chain. We could start with this guy being carbon number 1, which means this guy's carbon 2, this guy's carbon 3, this guy's carbon 4, this guy's carbon 5, that's carbon 6, and that's carbon 7. So that's one way we can name it or number it. The other way we can number it is, frankly, going the other direction. We could call this guy carbon number 1. We could call this guy carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, and carbon number 7. So when you go to name a alkane like this, what you want to identify is the longest carbon chain. You then want to identify the groups that are attached, and you want to find the location. What carbon is that group attached to? In this particular case, no matter which way I go, which number of carbon is that attached to? Number 4, right? This group right here is coming in right here at carbon number 4, no matter which way you went, which does sometimes happen. But sometimes what happens is there is a difference in where the group's attached. Maybe in one way it's attached to carbon number 2, and maybe in the other way it's attached to carbon number 4. When you number the chain, you always want to go whichever way the numbering gives the group the smallest number. So it's always the smallest number when you're doing organic chemistry. In this case, it doesn't make a difference, but there are definitely cases where it will make a difference depending on which way you go. So in this case, it doesn't really make a difference. So if we were to properly name this, this would be 4-isopropyl, because the 4 is the carbon where the isopropyl group is attached to. And then the rest of the name is heptane. Maybe if it writes heptane. So this would be 4-isopropyl heptane, and that would be the proper name for this guy. When we write names in organic chemistry, we always put a, and we're going to talk about this a little bit more in just a second. We're kind of jumping the gun here, but we always put a dash between a number and a letter. So that is why the dash is there between a number and a letter. And if you had two numbers together in a name, which can happen, we put a comma between them. So we put a comma between two numbers in a name, and a dash always between a number and a letter, or a letter and a number, however that goes. You know, you got one of each. We always put a dash between them. First off, any questions on any of that? Yeah. Yeah, so let's just say we let's see here. Let's just say we had something like let's see something like this here. How's this? Too many H's there. All right, so let's start with this. First off, the longest carbon chain is how many in this one? How many is the longest continuous carbon chain? Try all your options, see which one is the longest continuous carbon chain. I agree, it is 6, yeah. So if we go straight across, 1, 2, 3, 4, 5, not too bad. Now we could then go 1, 2, 3, 4, which is less than 5, obviously, so that's not good. Again, we're looking for the longest carbon chain. Our last option, which sometimes is missed by a lot of people, is this option. 1, 2, 3, 4, 5, and 6 right there. Yeah. So again, the longest carbon chain may not always be the straightest. And that's why it's really a good idea to check all your options to find the longest carbon chain. Any questions on that? Now, since this is the longest carbon chain and it is 6 carbons, the base of the name should be 6 carbons is hexane. Yeah. All right. So again, that's why those first 10 are really important. Yes. This here that I highlighted is really the main part of the chain. What is attached here, again, is referred to as a group. And in this case, it's actually a carbon group. So it is sometimes referred to as a alkyl group. And an alkyl group is a carbon group that's attached to the main part of the chain, but not part of the main chain. So it's like a branch just coming off of the main chain. So an alkyl group is a carbon containing group that basically is different than the first 10 alkanes. And it is different than the first 10 alkanes because let's first take a look at this guy. How many carbons are on that group? Just 1, right? And 1 carbon that is a alkane is known as methane. Yeah. And methane is CH4, right? Now, if I wanted to attach methane to this group, this guy that I have highlighted in yellow, and I just drew a line to attach it to that guy in yellow, would that be problematic for that guy? How many bonds would carbon then have if I drew that line to connect it in? It would then have 5 bonds, right? Which is too many. This guy doesn't have 4 hydrogens. It has how many? 3. So what an alkyl group is an alkane that is missing a hydrogen so that when it connects in, it still has just 4 bonds. So this guy is a CH3 group where it is missing 1 hydrogen. That allows it to connect to the main chain without going over 4 bonds. Yeah. Everybody see that? Yeah. So the CH3, which is a group missing 1 hydrogen from the methane, which is not a group, it's an actual organic compound, but it needs to lose that hydrogen to allow it to connect in and not have too many bonds. I remember I said everything goes back to those alkane names. So does the group name. This is an alkyl group that ends in YL. This is methane. You drop the last part and this CH3 becomes what is known as a methyl group based off of methane. So a methyl group is basically methane with 1 less hydrogen that allows it to connect in, and that's how you would name it. It is known as a methyl group. If I had 2 carbon group that's missing 1 hydrogen, it would not be ethane, it would be a full group. If I had a 3 carbon group that's missing a hydrogen and is part of a group, it would be a propyl group, YL. So you go back to those 10 names for the groups that are attached. That are not part of the main chain. And that is how you would name that. And first off, any questions on that there? Let's do that now. So hopefully I drew this right. And I was just trying off the top of my head. So I'm going to take a moment here and hope for the best. All right. So now that we're back, we're going to number this chain. And there's 2 ways to number. We could start up on top and go around. So I'll do that in blue. This would be carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. This would be carbon 5. And that would be carbon 6. The other way that we could number it, I'll go around and do it in green here, starting at the other carbon, the other end, basically. This would be carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. That would be carbon 5. And that would be carbon 6 in this case. Is there a difference now where that group is attached? There is. Going the blue direction, it's attached at which carbon? 3. Going the green direction, it's attached at carbon number It is as simple as 3 is less than 4. Yeah, so we would want to go in this case. The blue direction to number this would be the correct way, because in this case, the group here gets the priority. So the group gets the priority in terms of the numbering, that we want to go in the way that will give us the smallest number for that group. So the proper way to number this would be not this way, but would be going that way. That means that our group there, I'll use the blue arrow, would be good. Our group is at carbon number 3. So now that we know the longest chain is hexane, we know the group name is methyl, and we know what carbon it's located at. That's pretty much all we need to name it. So we start with the groups. If there happens to be more than one group, it is named in alphabetical order, regardless of number. So alphabetical order for the groups, regardless of number. So in this case, there's just one group, and it's at carbon number 3, which means this would be 3-methyl. Once again, the 3 is where the methyl group is located, and we do need the dash between the number and the letter. And what's left at that point is just the main chain, which is known as hexane. So this would be 3-methyl hexane. Question. The first day, it gets better. I don't know. Look, I'm having organic flashbacks. It's all right. Any questions on that there? Yeah. All right. So I hope that answered your question. Again, it does make a difference. And you, much like when you're looking for the longest carbon chain, you want to kind of check all your options. When you're doing the numbering, you do want to kind of look at it from both directions. Again, like the first one I did there, it is possible that it doesn't really matter which way you go. It will end up at the same number. But there's a lot of times like this where it does matter. By the way, when you choose a direction to go with, you got to keep that direction for everything that's attached. So for example, I'll just edit this guy here. If we had another group, say, we'll get rid of that hydrogen, and say we had like a bromine hanging off over here, which would then be another group that's attached. Because we determined going this way, the blue direction was the lowest number, which it would actually still be in this case, right? Because that would now put the bromine at carbon number 2, right? Versus if we went the other way, 1, 2, 3, 4, 5, going the opposite way. So that is still the lowest direction. So that would then be 2-bromyl. By the way, halogens, bromine is bromol, is how you name it. Chlorine is chloral. Fluorine is fluoral. As to how you kind of name those halogens, chloral, bromo, fluoral is how you kind of name those. But you do it the same way. In this case, it would then become 2-bromyl, 3-methyl hexane. You would just add them all in there. So in that case, I guess what I'm trying to say here for this one is if you choose a direction for numbering based on the lowest number, everybody else that's attached got to be numbered in the same direction. So you can't choose one way for one and the other way for the other. You got to pick one way of numbering the longest chain that should be the smallest number for everybody that's there. And you got to stick with that numbering for everybody that's attached, because there will be things that have multiple things attached to the main chain, not just one thing. So you have to make sure you stick with the same numbering for everybody that is there. Any questions on that there? All right. I feel like we jumped several slides in this thing. So let's just try some more while we're into naming already, I suppose. Why not? All right, let's just draw some here. I'm just going to randomly draw things and hope for the best. That looks good, I think, maybe. Let's see what I drew. All right, I like it. I don't know. I like it. Give it a shot. I'll give it a shot. Give it the old college try, they say. All right, so why don't you try these two here and see what you come up with here. Okay, so since we're getting there, let's take a look at these here. So on the one on the left, the longest carbon chain should be somewhere about there, yeah? That is 1, 2, 3, 4, 5, 6, 7 carbons, which means the base of that name should be 7 carbons, which is heptane. That's like the base of the name. We have this guy that is attached not on the main chain. That is 2 carbons, which then becomes a alkyl group, right? So 2 carbons that's not a group is ethane. So this guy, which is a group, becomes a ethyl group. Yeah, so that is a ethyl group, 2 carbon group that is there. Any questions on that there? We need to number the chain. We have 2 ways that we can number it, going kind of starting up here. This could be 1, 2, 3, 4, 5, 6, and 7. Going the other way in terms of numbering, this would be 1, 2, 3, 4, 5, 6, and 7. Which way is the smallest? Doesn't matter in this case. It doesn't. Each way gives us 4. So that's really all we need. It's at number 4. It's an ethyl group. And the main part here is heptane. It all goes together. I just kind of spaced it out there, but it would be 4 ethyl heptane. Again, the ethyl and heptane would all be together in one word, basically. Yeah. Question? It will always be an alkyl group if it's just a carbon containing group. Yeah. And it will be based off of those first 10 alkanes, drop the last part of it, and add YL to the end of it. It's 4 ethyl because that is the carbon at which this group is attached. And in this case, it doesn't matter which way you number it. It ends up at carbon number 4, either direction. Yeah. Yep. Other questions? All right, looking at this one here, you should have got like this move, perhaps, yeah? 1, 2, 3, 4, 5, 6, 7 as well. I guess I got 7 carbons on my head. That is heptane. There you go. That means in this particular case, we actually have a couple of groups, right? We got this guy, which is a group, and we got this guy, which is a group. This is a 1 carbon group, which is based off of methane, but because it's a group, it is now a methyl group. This is not a carbon group, which was the question a second ago. So this would not be named off of those first 10. This is one of the halogens, which would be known as bromo. So that would be the name of that group. Now that we have our groups identified, we need to do our numbering. So starting up here, 1, 2, 3, 4, 5, 6, 7 are going the other way. This would be 1, 2, 3, 4, 5, 6, and 7. Going in the blue direction, both groups are at 4 and 6, I believe. Going in the red direction, we have a group at carbon number 2 and a group at carbon number 4. It is as simple as which one is the smaller number? 2. So 2 and 4 is the correct way of going. We would number in this direction. It's as simple as 2 is less than 4, basically. Yeah, this is basically what you needed there. Now that we have it, that basically means this is going to be 2-bromo because that's the carbon where it's at. This is going to be 4-methyl because that's the carbon where it's at. And now we're ready to put this together in alphabetical order, regardless of number, which means B comes before M. So B before M. Putting all those guys together, that gives me 2-bromo dash 4-methyl. And the last part of the name is heptane. It is all about location of where you find everything. The 2 here means if you go to carbon number 2, you will see a bromine hanging out there. The 4 here means if you go to carbon number 4, you will find a methyl group hanging out there. And the longest continuous carbon chain is 7. So basically the name is nothing more than basically the locations. Any questions on any of that there? Once again, we have our dashes between numbers and letters, and that's why we have the multiple dashes between those things. Any questions?